So in the last few videos, then, I've given you most of what I've put together on this sheet. We look at the instructions on this side. Well, I guess first we've got the formats, right? We've got R, I, S, B, U, and J instruction formats. R for register, I for immediate, S for store, and that's a special one because we want to put the registers in the right place. B for branch, U for upper immediate. And so these are the upper 20 bits. And then J for jumps. Those are the standard formats in the base instruction set for RISC-V. And their equivalent immediate values that might be constructed if you have an immediate instruction. Then down here we've got the instructions themselves, the ALU instructions. We've got 10, I guess, register versions and 9 immediate versions. Then we've got our load and store instructions. Then we've got our branch instructions, we've got our jump instructions, and then we've got our system support instructions. We've got a system call and a bunch of other stuff. We've got our address construction, the upper 20-bit stuff, and then we've got a fence, which probably we won't use very often until we do pipelining stuff. Then in the middle here, I've got common syscalls that appear in RARs, RARs being the RISC-V assembler and simulator. And then the common assembler directives that you might use when writing code in RARs. I didn't mention we've got, this is a little 1, 2, 3, 4, 5 cycle pipeline that would be the sort of standard that would appear in RARs. And then we've got the control status registers, the privilege modes, and then on to the right side we've got the register file. I've got a little sort of typical conventional stack frame as a reference, and then common pseudo instructions. Now down at the bottom here are 2 extra bonuses because there's a bit of space left on this sheet that I'm thinking about what to put in here. These are a little bit more compact than I'd like, and I might mess them around a little bit, but in general what I wanted to add are the floating point extensions and the multiplication extensions. So these are here. So the floating point extensions add, this is sort of the base RISC-V is integer, but most of the time most people will want to do floating point, so it's a very common extension to add to the base RISC-V. It adds 32 more registers, so there's now 32 integer registers and a whole nother 32 floating point registers. These are called F0 through F31. We've got store and load instructions. This is a special format that specifies storing and loading into the floating point registers. And then we've got calculation, which has these opcodes and formats. The function code here is going to specify the rounding mode for floating point numbers because there's a lot of rounding mode complexity here. And these are going to look like this. So F add.s. So it's going to be F for floating point, and then the operation you're doing, and then you're always also going to have a size. So single precision, double precision, like that. You've got F add, subtract, multiply, and divide, and square root. You've got minimum and maximum. You've got equal, less than, and less than or equal to. So you've got comparisons, and then you've got these other things as well. And then you've got these really clever multiply, add, accumulate kind of combo instructions. Whenever we measure the performance of a machine, we usually measure it in flops, floating point operations per second. This is that operation. You're going to multiply 2 numbers together and then add that to a third. So this is multiply, accumulate. So a destination register gets 1 register times another register plus another register. 4 registers instead of 3. So 4 registers, 3 sources and a destination, and then you can have FMADD, so floating point multiply add, single or double precision, and you can also have the negative version of that, FNMADD, where the destination register is the negative of multiply and then add. And the same with subtract, right? You can have floating point multiply subtract or floating point negate multiply subtract. And then you've got a bunch of other stuff. Sign injection, you've got a bit copy, you've got instructions that convert from floating point to immediate and back. You've got a instruction that classifies the floating point number, whether it's a regular number, a denormalized number, a zero, a not a number, an infinity, right? All of those sort of special numbers in floating point that we know. And again, this is a pretty compact representation. I might expand that a little bit just to give you an idea. And then the other really common extension is the multiply extension, where these are usually R-type instructions, and what you get is two source registers into a destination, and you multiply them together. Now, the trick with multiply is that, and with divide, is that the result is twice as big as the input. So if you take two 32-bit numbers, theoretically, your size of your result is 64 bits. Now, most of the time, when you have two reasonably small numbers, you multiply them together and you can fit them into a 32-bit result. And so we have a special instruction for that, which is just regular multiply. Regular multiply assumes that RS1 and RS2 are both signed, and it assumes that the result can fit in 32 bits. And so you just take the low 32 bits of the result and put that in the destination register, and that's good for most of the time. You've got another instruction called multiply H, which is to take the high 32 bits. And so if you expect the size of your result to actually be beyond 32 bits, then you're going to want to multiply high, multiply low, and then you've got a 64-bit number that you're going to have to do something with. So the multiply extension gives you the capacity to produce a 64-bit number. What you do with it after that is up to you. And then the other interesting variant is that you've got ways to do signed times unsigned. So multiply by itself assumes signed numbers, and then multiply high assumes signed numbers. Then you've got multiply high SU for signed RS1 and unsigned RS2. And then you've got multiply high U when they're both unsigned. Now, why don't we have multiply when they're unsigned? Because an unsigned multiply only matters in the biggest version, right? If you're going to get up to 64 bits, you get that signed number up at the top there. So these are going to be signed, unsigned for the high version of these multiplies. And then you got divide and divide unsigned, and remainder unsigned. These are fairly standard. The result, you're still going to get 64 bits of result when you're dividing, but it's going to be a 32-bit quotient and a 32-bit remainder. And so you have two separate instructions, one to generate the remainder and one to generate the quotient. So that's the multiply extension in a really simple format, the floating point extension in a really simple format, and that's the whole sheet. That's the real basics of RISC-V. With that, I expect I should be able to ask you, what is the 32-bit encoding of some instruction? And based on the data that's in this sheet, you can tell me what the 32 bits for that instruction would look like.